There will be a quiz on the FinFitin protocol at the end of this lecture. And I expect it to appear in a call for papers, as well as a program guide and other paperwork by each and every neighbor here. If not, I will find you, I will hunt you down, and I will say, "Fuck you, neighbor." And you will say? "Fuck you, neighbor." There we go. So today's lecture is a new one. The idea is that for the past year I've been building a debugger of my own called the GoodFet. And there are certain vulnerabilities that I've found only because I've written a debugger from scratch. So the bulk of this lecture will be showing you in depth how debuggers work and how the different protocols vary. JTAG is the most famous one, but every chip has its own little quirks to it and its own spin on the debugging protocol. You have three that will be discussed in this lecture. I'll be discussing the MSP430's JTAG debugging protocol, as well as the ChipCon 2430's 8051 synchronous serial protocol, and another one for the atmel @tiny's. Is the echo bothering anyone else or just me? Okay. So this is TV Begone. Whoa. Okay. This is TV Begone by. Hello? Is it this microphone reacting with? I don't know. Yeah, so this is the @tiny85 in the TV Begone kit by Mitch Altman and Lady Ada. And is there a laser pointer I could use? All right. So up here on the right, you see the 6-pin port labeled ICSP? That's actually used for programming the chip. So if you buy this as a blank board and you populate it with your own parts, you have to also add a 6-pin header and then flash in your own code to it. This is the EZ430 by Texas Instruments. It is a debugger, but it can also be debugged itself. The 5 pins that I've brought out at the top can be used to reflash the MSP430, which is on the bottom of this board, allowing you to run new debugging software on the board itself. Last year at Congress, I presented a lecture on reverse engineering this board with the aim of writing a new application to run inside of it. In doing so, I got so fed up with the board itself that I wrote new software and hardware for it, and I'm able to do a complete replacement. The code, however, can also run on this board with proper patching. Here we have an unfinished project of mine. It's the GUSC 10. This is a replacement cartridge for the Sega Genesis and also the Nomad. I think it's called the Master System here, or Mega Drive. So this sticks into the cartridge slot, and it has an SRAM chip that it flashes before booting with a given game image. And then when you turn your game system on, you have whatever ROM image was loaded. If any of you are familiar with the Sega Genesis copy protection system, it's worth studying. It's based upon trademarks, not copyright law. So when they're trying to force all of their vendors to use their proper licensing and do it in the Sega-style cartridge, instead of having a proprietary library that they had to load or a copy protection chip, as Nintendo did, they actually just put their name in memory at a particular address, SEGA, in ASCII. If that exists in memory, then the cartridge is valid. And they thought that they could enforce this with trademark law. This did not stand up in the American courts. I'm not sure how it worked in Germany. My other project from Congress last year, and yet one more thing that can be debugged, is the BSL cracker itself. This connects to a JTAG debugger on the left, and on the right it connects to a target chip's serial port. And then it runs the serial bootloader on the target device, changing its guess of a password, looking for a 2 clock cycle difference, which is actually magnified by a difference in the clock rates of the chips. But this can crack the password of an MSP430 1 byte at a time, and it can narrow it down on it just like in the game Mastermind. Oops. This here is an IPv6 computer that also includes a radio. It's on a single chip. This is the board in my hand. If you can't see it, that's the point. These are wireless sensor networks. So you can purchase 100 of these. You can slap lithium batteries on them with proper power management. You throw them out in the wild, and they'll run for a year unattended. This is a development kit from Texas Instruments that actually has two different chips on it. There's the 20-bit MSP430 F427 here above the 4 on the left, the big chip. And that is the upper JTAG port on the left. The bottom JTAG port on the left has a smaller chip to the right of it. And that's actually SPI-by-wire, which is a variant of 4-wire JTAG that we'll discuss briefly. The reason why you want to build a debugger for all of these things is so that you can speak to them yourself without having a library or a product in between you and the device itself. If you have, say, a test environment working on your workbench, you have your gizmo, you can run your test case on your debugger, and you know that this device works. That's great in development. But as soon as you need to deploy that device and you need to run these test cases on an assembly line, you find yourself having to take your same Windows workstation, because the software isn't available for Mac, and it's not updated for Linux, and you have to stick it on the assembly line, and if it goes down, if it chugs up for an update, if it locks up for any reason, the assembly line stops and your product stops moving. And that's not acceptable. So in that regard, from a production standpoint, it's valuable to be able to have your own debugging code that you can put into your own device to flash the device yourself. You could make a handheld device with what I cover in this lecture, as well as the code online, which flashes a chip on a single button press. And then you could sit there on the assembly line and you could hit each unit, push the button, flash the firmware in, test it, and move on to the next. If you had 100 devices to flash, you could do this in a fraction of the time that the PC debugger would allow you to do it. Because you don't have to keep the window open and keep clicking on the button and all of that stuff. You can automate it. It's also valuable because you can start attacking these devices through their own debugging protocols. They will speak the debugging protocols even in their locked state, and you can sort of trick them into letting you go further than you're supposed to. So in last year's slides, I actually had two talks at Congress. The first was on repurposing the EZ430. The concept here is that you could take an existing TI debugger, and you could reverse engineer just enough of its firmware to know where to place the hooks, to know which port does what, to know how the clocks work, how the timing worked. And eventually, you could also use this information to build new hardware for the same firmware. And in articles since, which you'll find on the blog, I showed how to extract that firmware from the driver itself. So if all you want is the TI debugger, you can get that, and you can manufacture that yourself. And the protocol that it speaks to the PC has even been reverse engineered by myself and two other groups, one of which beat me to it. In my second lecture, I attacked a different debugging protocol of the MSP430. Could someone bring me a mate? The beer doesn't work on stage. Won't stop me from trying. Ah, danke schön, neighbor. Ah, mate. Cheers for the mate. And for Ola. So my second lecture centered around extracting firmware from a chip. If you have a microcontroller and it has a program in it, but the microcontroller is locked, how do you get it out? The method I demonstrated was by timing attack against the MSP430 bootloader. Ugh. Forgive my throat. And also the use of voltage glitching to skip a single instruction within that bootloader. So if the bootloader itself were to be disabled, you can skip around that by jumping, by skipping out of a self-referential jump. There would be a jump if 0 plus 0 instruction, which replaces the program counter with its old value at the end of execution. This requires 2 clock cycles on 4 clock edges to execute. And if 2 of those clock edges are skipped, you sort of fall into the next instruction and keep executing. And the next instruction is where you would go if the comparison went the other way. They don't do any buffering, so if you skip this one instruction, you can fall through. This is the the EZ430 that I reverse engineered. This is my device for attacking the MSP430 bootloader. The bootloader itself was not software that was added after the fact. It was actually firmware that ships with every single chip as part of masked ROM. This is a photograph of the ROM that I took with a microscope after removing the package of the chip using fuming nitric acid. Don't go shoot, neighbor. And then also the depassivization layer and just a hair of the metal layer to add contrast to the image using hydrofluoric acid. And you can see these different columns, each one of which is a bit of significance. It's been a while since I've deciphered these, but if I recall correctly, the battery's dead. Okay. The ones on the left are the least significant bit, the ones on the right are the most significant bit. And then within each column, if you pick any given position, that same position within all of the columns will give you a word. By taking a couple of the words and also reading it out of firmware or comparing it against reading it by software, or by comparing it to different versions, you can identify where all of the bits reside. But that was the old stuff. The new stuff involves writing a debugger. First, for the ChipCon 8051, I'll be discussing how to debug it and how to glitch into it. I'll be discussing how the protocol works, exactly which bytes you send and which bytes you receive back, as well as as yet unpublished crypto vulnerability that I discovered for ChipCon's Zigbee radio stack. So if any of you have been playing with the smart grid, this lets you guess a session key. I have two 32 kilobyte lookup tables which contain every session key used by one of the most popular stacks, the ChipCon Z stack. Hopefully they'll have that patch soon, and the vendors that use that code will patch it soon. They've already been informed, but so far as I know, there's no patch out yet. I'll also be discussing MSP430 JTAG debugging, which is interesting because it's incompletely documented. The protocol is out there in the wild. You can get a copy, you can get a debugger, you can hook it up to a chip, you can debug that chip, and you can watch it with a logic analyzer, and you can decipher what the words of the instructions mean, but they haven't told you the one piece of secret sauce that you need to make a full debugger, which is breakpoints. There's nothing in the documentation that describes how to halt on a given instruction or how to halt in the software breakpoint, which is where you have an instruction that forces a halt. If anyone has this information, I would love for it to appear in my inbox. You would be quite neighborly for doing so. And I'll briefly discuss the Atmel AVR's protocol, because I've been working with glitching it using these quantitative tests. So I run through a debugging session, and during the initialization phase, I will drop the power sharply to a low value and bring it right back up. And I keep doing this repeatedly. I'm varying the time and the voltage, and I'm also just trying to run it at low voltages to figure out where it fails. The idea is that these two graphs should overlap in some regions. So, for example, there's a local minima where the stability of the chip gets really bad at low voltage. It's better at a lower voltage than it is at this one. And I've also found that that same point is where the chip is likely to let me skip its debug fuse. So if Mitch was not so neighborly about sharing the firmware to his TV Begone, and I wanted to extract it forcefully, I could do so by dropping the voltage during the initialization phase when it's actually reading this security fuse bit out. I won't be discussing some of my older projects, and I won't be going over the schematics in detail because they're not that complicated. You have a USB to serial chip talking to an MSP430 microcontroller, which runs custom C code. It has a bunch of digital I/O pins for talking to digital I/O pins, and it has a digital to analog converter with 12 bits accuracy that it uses to power the target. You can just write a value into that register and immediately raise or drop the target voltage. In previous lectures, I discussed Zigbee stack overflows for actually injecting codes into a running wireless sensor node. I won't be doing that today, but you can find the details in my TIDC of '08 lecture. It's the Texas Instruments Developers Conference. I won't be discussing the timing exploit itself, but you should look up those lecture notes and the slides, because it's a really neat trick that allows it to work. Or reverse engineering the debugger, or hacking a smart meter. And while I'd love to talk about HP28 graphing calculators, I don't have time. So this is a debugger itself. You've got a couple of plugs on the front that you run into the target board. On the back, you've got a USB plug or Ethernet, which runs to the host computer. The idea is that it reads, writes, and erases memory. It lets you trace the program counter. So you could do an execution trace of an entire program, single-stepping it and recording where it's been so that you know where to optimize. You can observe registers, and you can start and stop on breakpoints. All the things that you would expect a debugger on a PC to do. The only difference is that the device you're debugging is external to the computer. It's running in a box somewhere on your bench, plugged up to things electrically. This is my debugger board, the GoodFet 20. Since then, I came out with the GoodFet 30, which is a cheaper variant. Then I found out that there's a global shortage of the cheap chip that I used in the GoodFet 30. So the GoodFet 21, which has just now been manufactured, is a descendant of this design, which is more powerful. The chip at the top was used for glitching. It's now irrelevant. All that remains are the chips on the bottom. The one on the left, near the USB plug, is just an FTDI USB to serial chip. It connects to the MSP430 to its right. The 430 has a built-in bootloader, so you can very quickly flash this repeatedly, and you don't need to have firmware loaded into it. So you don't have the chicken and egg problem of already needing a flashed microcontroller just to make a new one, or to make a flasher. JTAG itself is used for a lot more than just the MSP430. It also targets the ARM, the PowerPC, UltraSpark. The OpenSpark chips have their own JTAG implementation, and you can run this very powerful CPU through. I haven't played with that chip in detail, but it would be really neat to get execution traces as it breaks them down into superscalar. So on more modern chips, you've got multiple instructions executing in parallel, which is what allows you to get more than one instruction per cycle. You might be able to halt it and then dump the micro-operations that come out from that buffer. But the details of how this works are unique to each family. It would not make any sense for the OpenSpark or another superscalar chip to have the same debugging protocol as a 16-bit microcontroller, like the MSP430. So each one is different. And they usually involve just pushing an instruction somewhere into the execution pipeline, or ring in the case of a multi-cycle chip. AVR ISP is a sort of secondary protocol for the Atmel AVR. They allow you to program either by JTAG, which supports debugging, or by ISP, which is only for programming. And then a lot of chips, particularly custom system-on-a-chip devices by radio companies, like ChipCon, they create their own debugging protocol, or it comes with the CPU core that they choose. So some of these things don't even have names. The ChipCon 8051 documentation is the debugging protocol of the ChipCon 1110, 1130, 2430, 2530. They just list part numbers in a series because they're so different. We've been over this. Just remember that if you don't build it, you don't really understand it. So the code for this device is split into two fragments. The idea is that anything that needs to have a fast reaction time. If you're trying to read a byte out and make a decision based upon that byte, the USB delay is suicide. And that's why even today you see so many products being shipped for the parallel port. It's because the parallel port has a faster reaction time. This gets around it by having C firmware running on the microcontroller, which speaks to Python on the PC. You begin by writing the lowest level functions in C. This might be as low level as setting a port or clearing a port, writing a byte, reading a byte. And the high level functions begin in Python and then move down into C, until eventually you have a C function that flashes an entire page of code. And then you can just slam out a large packet through the USB buffer into the target, or into the MSP430, which actually does the programming with the target. This is how fast programming works. The protocol itself is as simple as possible. You have a single byte for the application. You have a single byte for the verb. The application might be for the monitor, if you want to read and write the memory of the debugger itself. Like if you want to check its version number, you actually just grab a value out of flash memory. If you want to know which chip is in your version of the debugger, you can just grab its model number out. There's a different application for every target. So you set this byte to a different value if you want to target an MSP430 or an AVR, and all of this code resides in parallel. There's no advantage to keeping it separate because there's enough flash memory to hold all of it, and the code is being executed directly from flash memory. This is not like a PC where you have to copy things to RAM first and then execute them there. And being written in C, you don't have the overheads of proper class inheritance and all of that stuff. The code also becomes a bit of a spaghetti mess, but that's manageable. And then after the verb, you've got a 16-bit length and then some data of up to that length. As a matter of courtesy, the Python client will check to make sure that there's enough buffer space for whatever it's about to write in. The firmware is written mostly in C with a little bit of assembly, and been over this. The only things to stress, though, are that this whole thing runs in less than 400 bytes of RAM. Everything else can stay in Flash, and everything in Flash we don't have to worry about. The limit for the mass production cost of this device is that if it ever goes above 512 bytes of RAM usage, the price of the chip almost doubles. So that's a hard limit that I'm trying to stay under, such that I can continue to manufacture these with the cheap chips. I've got versions at 3 megahertz and 16. This is a lot less powerful than the PCs that you're used to. Also of note is that every instruction takes a fixed amount of time to execute. Some instructions take more than others, but you don't have to worry about multitasking or threads colliding or anything like that. The client, written in Python, does mid-level and high-level. So the first chip we'll talk about is the ChipCon 2430. This is an 8051 microcontroller, which was one of the very early single-chip computers out of Intel. It works with single-byte opcode, optionally followed by parameters. You can actually write this machine language or read it by using lookup tables on paper. And it's used for very small IPv6 implementations. This is the device here. You can actually give it an IP address and ping it. This is it on a keyboard. That little chip in the middle is the entire computer. RAM, ROM, flash, EEPROM, everything. It's documented in a 16-page document from its manufacturer. It uses an SPI-like protocol, meaning that you've got a clock. Each party writes on the rising edge and reads on the falling edge. But the data line here is bidirectional. So the very last word can switch directions, allowing data to come back from the chip to the host. This is what it looks like on my high-tech chalkboard. I don't have a chalkboard anymore. I miss it. To start the debugging sequence, all you do is pull the reset line low, which sort of suspends the chip as you're about to reboot it. And then before you raise it high, you send 2 pulses on the clock. Once you're in, the sequence is that you send a single command byte along with 0 to 3 data bytes and 0 or 1 return bytes. And this is all encoded in the command byte. So if you look at the 5 most significant bits, that's the instruction. There's a single bit that describes whether or not there's a reply, and there are 2 bits that describe how many parameters you're throwing after. If they're 1, 1, you send 3 bytes. This is how the data looks on the wire. You send the most significant bit first. Each party will write a value on the rising edge, so you'll see that the rising lines are parallel, and then it's sampled on the falling edge, and you'll see that there's never a transition on the lower signal, the data signal, as the clock line is falling. And that's how data errors are prevented. This is a list of the commands that are supported. I won't enumerate them. But worth noting is that the very first command is number 2. 0 and 1 come before it, and they do something weird. There are also a couple of extra commands that might fit after get chip ID, because the command space isn't filled. I think that it is filled internally because in a later revision of this protocol, they renamed one of the functions. This pointer doesn't work very well. There's a step replace instruction. Here's a clearer list for you. Step replace was actually replaced with a new instruction that does DMA transfers to the chip for very fast programming. And they had to remove this because they filled up everything else. I haven't yet checked those others, but it's worth looking into. So in this command list, and I'll jump back to it for just a second, you'll notice that there's nothing that directly reads or writes memory. And there's nothing that writes the program counter. So if I go back here, you see you can read and write the configuration register, you can erase the entire chip, you can get the program counter, but you can't write any of these things. The reason you can't is because you can do the same thing by debugging machine language code. So you actually use debug instruction to run individual fragments if you want to read or write RAM. And if you want to read or write flash, you just write a bunch of executable code into RAM, and then you jump into it, and you let it do its thing. This is the function that actually reads a value out of internal RAM. The 8051 has 3 or 4 memories, depending upon how you think of it. There's internal RAM, of which it has 256 bytes, external RAM, which can be up to 64 kilobytes, and code memory, which can be 64 kilobytes or more if they have banking. So the first thing that I do is I clear the accumulator. And I do that by executing E4. And 0xE4 is clear the accumulator as an 8051 byte instruction. If you put that into a machine language program, it will clear the accumulator. And it takes no parameters after it. The next thing that I do is I move the value in memory at the address I'm interested in reading into the accumulator. And then I wait a couple of clock ticks after. The first parameter of the debug function, ccdebug, that describes how many bytes I want to send, but it also tells how many clock edges I want to hit. So even though this 0 at the end is not part of the instruction, it's necessary for me to get the accumulator value back. And that's how I read a value out of RAM. You can do the same thing to write flash memory. You do it by writing all of the page that you want in flash memory into RAM, and then copying it in bulk using a program that you've loaded into RAM after it. And they provide an example program for you in the documentation. So this is what the program looks like. You actually just have comments and bytes. And then on the far edge in comments, you've got the meanings of this. So if you flip between the two on a wide display, you can actually see both the machine language and the disassembly. And if you take the time to do it, you could even write this fragment in C, having a compile and then link into the debugger. There's a security feature of this protocol, though. And it's the security features that make these things interesting, because you have to have something to break. You have to have a challenge. Here, the debug lock is read as the chip turns on, and it's required for halting and resuming the chip and for running your own instructions. So the idea is that you can't read or write memory unless the chip has not been locked. And you can only unlock the chip by erasing the entire chip. And this is part of the status register. If you set the debug lock, you're writing a bit of EEPROM that gets erased during the debug erase, but it doesn't change that status register bit. So you can actually lock the chip, then program it, then power it down, and it's locked and ready for distribution. At the same time, if the bit is read wrong at startup, it stays wrong. So if you load it up with a bad power supply and it fetches the wrong bit out of that EEPROM, you stay in. You can read and write memory till kingdom come, and it's only at the end, when you power it down, that you're locked out. There's another mistake, and this one I published in the summer. You can erase the chip first and then read it, because the chip erase command only erases flash memory. And this is very common. Erasing flash memory and erasing RAM are very different operations. To erase flash memory, you have to build up a charge pump, you have to start a clock, the clock has to hit the flash in proper sequence. And instead of doing that, it's a lot easier to just erase flash memory, because that's where the secrets that the vendor is concerned about reside in. If I get flash memory, I can plagiarize a design. And that's what they're worried about. That's what they're defending against. In the same way that on your PC you might defend against malware. The problem is that these devices are now being networked. So when you throw one of these on an IPv6 network, and it has keys, and those keys are stored in RAM, they can be extracted from the device by erasing its flash and reading out its RAM. You have one dud device that costs $10 that's meant to be disposable. The attacker has your keys. And there's no way to patch this. There's no way to keep RAM from being exposed. You can replace the firmware to not store the keys in RAM, but that becomes very difficult with things like session keys. And reflashing the chip for every session key is not manageable. So to erase and then dump, all you do is erase the chip, copy out its RAM, and then search that block of RAM for the keys. To glitch it until it's unlocked, all you do is keep re-entering the chip and hit the voltage rail with spikes downward. Keep dropping its voltage low, and I'll show you later how to figure out exactly how low. But the thing that I kept getting in reply to this, to that old stuff, was this Florida regulation and similar laws that you're not allowed to tamper with the device. That there's some holy grail about physical interaction with the target. An attacker can never set foot on your property. He can never open up the box. He can never get a screwdriver or a logic probe or anything like that. So I said, OK. And I started playing with the Zigbee stack software using the debugger. The Zigbee stack uses, the Z stack from ChipCon, uses a hardware pseudo-random number generator, which is seeded by a true random number generator in the radio. The seed state, I think, is sufficiently random. I don't know that it's perfect, but it's pretty damn close. The pseudo-random number generator, though, has a really small seed. Its entire state is 16 bits, and half of the bits are being skipped. And when you try to test this, you can't just recompile the code, because it uses a chip-specific hardware device. It's not calling this LFSR function. It's writing a value into one register and reading a value out of another, like a magic address in RAM that just happens to have a function attached to it. And you can't simulate it unless someone has added this feature to a simulator. What you can do is debug it and trace it and copy it out that way. So I used Wine to install the publicly available demo of this software. Once I had it, I wrote this dandy little code in Python. All it does is run through RAM and copy bytes out to a file based upon tags that are placed in RAM. So I've got dead or beef in an address. Dead means it's ready, beef means it's not, or vice versa. And I just keep freezing it and releasing it until I get my values out. On the C side, this is on the target, this is not on the debugger. I run a C program on the chip that calls the library that I'm interested in auditing. This C application runs on the target itself, and it's running the actual demo code that's shipped with the chip. I'm using a different compiler, but aside from that, it's the same thing. And I put this little fragment of machine language in. A5 is not a valid 8051 instruction. It's the only opcode that is not defined for the 8051. Everything else means something. A5 was left to be chip-specific by the instruction set designer. And for good reason. He thought if they had 10 extra instructions available, people would use all of them. But if he left just one, and he left instructions that it never be changed or defined to be anything, then that might survive. So A5 is a software breakpoint. You call that at the end of the loop, and it will wait for the debugger to restart the application from exactly where it left off. So in each iteration of the loop, you just wait for a while as the debugger copies all of the values out, dumps them into a file, and then you can continue on. This is a histogram that I generated of the hardware random number generator. You'll see that the byte as a whole is not the least bit random, but if you look only at the least significant bit, it actually does appear to be rather random. I won't say perfect, because there's a much bigger issue. The pseudo-random number generator has 1 byte per tick, so it's actually going through 15 bits of its address space. And these are the bytes that I dumped by the debugger. This is from hex dump to head. So all of the bytes that you see here are the very beginning of the dump. And I took that beginning, and I just grabbed a couple of bytes at random, and I grepped for them with color. I love this switch. So you see, there are the bytes, and there they are again, and there they are again, and there they are again. And the difference between them is 2 to the 15th power bytes minus 1. That's just a little bit more than 32,000. And you can try every AES key in this range in very short time on your PC. There's also a dandy AES accelerator in every one of these chips. So if you had a worm that was trying to spread through them, any chip that had been infected could be used as a computational node with hardware acceleration to try and break the rest. And it also has the random number generator installed, so it doesn't need this list. It can generate it itself as it's needed, just feeding them into the AES register until things make sense. The usage in the Zigbee stack is that they've got this function keygen, or it has a longer name. It just takes a pointer and a length, and it populates at that pointer with length number of random bytes from the getRandByte function. And all this does is call the low or high word of the PRNG, and then clock it once more. Now, which word you get is determined by the starting state. And the starting state is random. So it will actually choose one of 2 32 kilobyte cycles, and it never jumps between them. So you've got 64 kilobytes to look through the first time. For any guess after that, you've only got 32 kilobytes to look through. Or, if they're generated in a row, one will be right after the other. It's quite convenient. So the idea is that you've got all of this stuff that doesn't seem to have that much to do with security. All of this general development stuff for legitimate engineering value, in the same way that in order to do computer security work, you have to have a good compiler. You have to have a good command line, a good text editor, when a text editor itself has very little to do with security. Here, the tools are often unavailable until you bother to make them. This platform that I'm making, though, is open under the BSD license and beerware. And if you want to rip me off and put anything else on it, we have the fuck you neighbor protocol. So if you steal it and you put it in a commercial product and you pretend that I had nothing to do with it, and then later on you get sued and you point them back at me, you can say, fuck you, neighbor, and I can say, fuck you too, neighbor, and we can high five. This is the next chip that I want to talk about. And I've got to speed up. I have too many slides. This is the MSP430. This is an early prototype that I got. And I like this chip because it's windowed. You can actually see that there's a chip inside. They didn't do this because they wanted to. They did this because it helps by UV erasure. So you have to stick this thing in a UV oven for half an hour, and when you take it out, all of the bits have become ones. You can move them back to 0, but not up to 1. This is a more modern board. And they have a really cool one that just came out as a Zigbee wristwatch using a descendant of this chip. So for $50, you can get a chip that will run as long, or a watch that will run for as long as any other wristwatch. But it also speaks to computers around you, so you can have it announced to your workstation that you walked into the room. And unlike the Zigbee watches, you don't have to recharge it every day or lug around a heavy battery. So back to JTAG. Even within a family, like the MSP430, you have variants between protocols. The MSP430 classic protocol is actually from the first flash generation of their chip, which was the first that could be programmed by JTAG. It was a 16-bit chip, by which I mean instructions are 16 bits wide, and so are pointers. The MSP430X is a 20-bit chip, which allows for 20-bit pointers. This creates an awkward situation in JTAG because you've got registers that you have to put pointers into, and their length matters. So they did a neat little trick where they kept all of the commands the same length. They just made the extra bytes come last. So when you're shifting in a 20-bit value into the MSP430X, you send the low 16 bits, most significant bit first, then the high 4 bits, most significant bit first. So you've got to like, shuffle everything as you move it in. There are also 2 line protocols, which only differ in how many pins they use and whether or not they're multiplexed. So JTAG itself uses 4 wires, while SPY-by-wire uses only 2, and it has a sort of meta clock that switches the 1 data line between the 4 wires of the traditional protocol, even changing its direction when it becomes output from the chip to the host. Inside of JTAG, you have 2 direct registers, an instruction register and a data register. And the data register can change by which instruction register you've chosen. So even though it might seem to make more sense to do things backward by loading the data first and then calling the instruction, as you would in reverse Polish notation, what you're actually doing is choosing where the data goes, and then the action once the data is loaded is based upon the position at which the chip is already at. And this is all a hardware state machine. There should be a lecture on day 4 that'll go into that in more detail. And read that guy's paper in the proceedings. It's worth your time. JTAG itself has these low-level functions. You're either shifting a value for IR, and I say shift because you are writing a new value in at the same time you're reading the old value out. You can't just write and you cannot just read. This isn't very important until you consider that the action happens at the end. So you can never leave the value in the register and hope to grab it later without recommitting the action. Like, if you write an instruction in and then you read it back out, you're just going to cause that action on the other exchange. There shouldn't be 2 DR shifts there. The other thing you might want to do is grab a chip ID. There's a single byte field that can be grabbed for every chip when you send a default command. And this is how you distinguish between drastically different chips. In the case of the MSP430s, even though you've got the 16-bit, 20-bit difference between the MSP430 and the MSP430X, they revamped everything with the MSP430X too. So the commands that you send in order to flash the chip, the way in which flash memory works, they're very different. These are distinguished in that one of them sends 8.9 and the other sends 9.2 in hex. I might have confused those 2. But you're identifying the general JTAG protocol by a single byte, and then you figure out what the individual chip is by asking it in that protocol. If you hook a JTAG debugger up to a chip family that it's never been programmed to see, it won't know what to do. There's no specification other than telling it that this is family 5.6 or 4.2 or FE. So aside from the various standards, there's no global standard that lets you read and write everything. To halt the CPU on the MSP430, you load IR data 16-bit into the instruction register. You're choosing which data register you're writing into next. Yes? What? Oh, you're waving at me. It's a neighborly wave. Fuck you, neighbor. Say it.
Fuck your neighbor.
There we go. All right. So what you're really doing is writing 3FFF into the 16-bit data register. 3FFF is an executable instruction. It's a jump to itself repeatedly. What this does is halt the CPU. It gets it into a state where it won't fail in the middle of an important instruction. And then you put this magic value into the control register, and that actually sets the halt bit to freeze the CPU. And in between, it executes just enough to jump back to itself, so it wakes up at the beginning of the instruction that it intended to next be executing, and it can resume again. Now, all I want you to get from this is that this is really machine specific. 3FFF does not mean jump to self on any chip except for this one, or any chip family except for this one. So lots of things in the protocols won't make sense until you understand the family thoroughly. This does involve reading the family guide and actually writing out machine language on paper, figuring out what the bit fields mean and the opcodes and all of that stuff. This is how you set the program counter. And you're doing something similar. You're just doing a move immediate value into the program counter. To write a flash word, you write the word itself to the address, then you return to read mode, and then you pulse. And this pulsing becomes important because it lets you directly control the flash memory. Have you heard that flash memory has limited life, but that it's really long, so you probably won't hit it unless you use it for flash? Well, that's true, but it doesn't have to be true, and you can control that here. So you're supposed to pulse it 35 times at between 257 and 475 kilohertz. When I was writing this, I thought, it doesn't matter, I'll try anything. I blew up bits. They're now permanently 0. And page arrays work similarly, except you're raising them up from 0s to 1s. Flash is 1s by default, and you write it to be 0s. So this creates a bit of an awkward thing in that how fast you talk to the target chip actually determines whether or not the write is successful. If you take the code that works at 3 megahertz and you run it at 12, it doesn't work. And it might even damage the target. Usually in computing, you don't have to worry about damaging anything. You don't have to worry about anything being probabilistic until you get to network optimization and stuff that's really complicated. Here you do. This is one of the first times I encountered in security that probability theory mattered, and it scared the living hell out of me. So you can burn bits for steganography. You can write a bit more or less thoroughly than you need to. So you can actually store more than 1 bit per bit. Suppose James Bond is crossing a border, and he's got a flash memory stick, and he knows that he's going to get searched. I've only shown this for a 16-bit microcontroller, but let's assume it scales up to gigabytes. What he can do is actually burn in his secret message, force the bits to stay 0 or make them lower than the other zeros, and then he can give up his thing for imaging. And the good data forensics guy who has his proper tools and maintains his chain of evidence is going to make a perfect image of it, recording every 1 and every 0 as it's read then. James Bond then slowly erases it, shaving the chip back up to 1s, and some of the 0s will turn to 1s before others. And that's how he sees his real message. I don't... thank you kindly. So in this day and age, it's a lot easier to just post a torrent file if you want to sneak something across a border, but this is still a neighborly little trick. And you can also use this for exploits. This is where it gets really fun, because there's this concern about, what are they called? Factory supply chain attacks, that's it. So the idea is that an attacker might sell you source material or might mess with your factory in order to change how your product turns out. So if an attacker controls the factory that's programming your smart cards, he could write a virus in there with the smart cards that allows them to give up their key. So you've got your smart card, you think you're secure, you use it for door access, the door just stole your key. You don't know. So what you can do is you can burn an exploit into an unused region of the chip. So at the end of flash memory, you write your little exploit, and then the beginning of flash, where the program begins, that all comes from the compiler. That's all fixed. That's all predictable, so you know which bits to make lower than others in order to change the code to jump into the later time. 10 minutes? Great. So the idea is that you can actually take a chip that you know will be written with firmware built with a particular compiler and nothing else. And you can say, jump into the bootloader if the 5th pin on the 3rd port is high and the 3rd port on the 5th pin is low. And then it will jump into the bootloader when that happens. It might show up as a small reliability issue, but unless anyone is reading the code out, and in a locked chip they might not, and it takes time to verify the code. So often this is skipped during programming. This lets you sneak a rootkit into a chip as it's being manufactured and locked. And once it's locked, you suddenly need a tool like the GoodFet to show that it's been tampered with. You can also do fuse glitching. So on the MSP430, there's a physical fuse that's broken. And It's broken with high voltage. It's physically damaged, at least in the older ones. They changed this in the new generation. And at startup, you're supposed to run through a fuse check. There's a 2-bit register. 1 bit tells whether or not you've attempted a fuse check. The other one tells whether or not that fuse check was successful. When you voltage glitch, they sometimes jump around. And when they jump around, the rest of the JTAG state is also knocked out. But you don't care because the JTAG state machine is designed to be recoverable. From any point in that state that's valid, you can navigate back to the beginning. So here, instead of performing the entry sequence, glitching, and then seeing if it was successful moving back to the beginning, you could actually glitch, see if you wound up anywhere, if so, move back to the beginning, and then test to see if it works. So even if you wind up damaging every single register's value in the chip, except for a couple of toggles that knock things out of whack, it'll let you through. On some models of this chip, if you try to debug them without a decoupling capacitor, they'll fall in accidentally using the official debugger. Here's the fuse check sequence. It's the same as the other, except that on the set TCLK line, the second one that's noted, at that point, you're not allowed to debug the chip, but you are in the state machine. It's only after the second one that you're allowed to move forward. If it denies you, it just forwards all traffic to the next chip. Running low on time, so I'll skip through ISP debugging, except to point out that it's very similar to the previous chips, except that it really has a lot of awkward bytes that can come out of sequence or out of order. And a good way to get around that is to actually graph what the thresholds are. So if I have this chip and I'm lowering the voltage on it, at what voltage does it fail? If I look this up in the data sheet, they give me a single threshold. That's not what it looks like. This is what it looks like. This is the probability that I can successfully read the model number from an unlocked chip. Why is there this local minima? Why is there a local maxima next to it? What else does this correlate, and how does this affect the low voltage that I need for glitching? Because I've been choosing these at random prior to this. I've been working on getting that to work at the same time that I've been testing these devices to ensure that I don't break any features as I add new ones. Because you've got lots of incestuous C code. You have functions calling functions that they weren't designed to. The JTAG 430 module calls code for the JTAG module. So what you can do is you can set up a regression test server, and you can just graph everything. And this is really cool because you can do things like graph the stability of chips in the face of multiple failure modes. I'm controlling the voltage and graphing the probability of success of trying an action for 4 different actions here. And I can get this graph with 10,000 samples on each, and it all happens in Philadelphia while I'm out here having fun in Berlin. And with enough samples, if I want to extend this out on another axis, if I'll wait for a month, I can get this in 3D, with the third axis being the time at which it glitches. Then, once this new graph is complete, what I expect to see is a line right here, looking like a mountain on the 3D graph, where like the depth dimension is time, that shows me exactly where it's most likely to glitch. And if I find this correlation, that will then mean that you can go from the cheap, easy-to-generate graph to the complicated one that tells you how to actually get into the chip in like an automated fashion. You can measure the simple thing and use that to figure out where the complicated thing happens, so the rare event happens. And then you don't have to wait overnight for the chip to be glitched into, as the AVRs sometimes take. You can just do it in a couple of minutes. So anyways, there's a bunch of other crap here that I don't have time for. But do catch Felix Donkey's talk on day 4 in Sol 1 at 1400. His paper is interesting. And if you'd care to help, I've got all sorts of stuff to do. The other thing is that I have free GoodFit boards. I was supposed to have them here. I don't. I'll mail them to you. They are free, but I do like Clubmata and PayPal. You can grab my articles on travisgoodspeed.blogspot.com. That's my email address. And glitching itself is not my idea. It's been done by satellite TV hackers forever. I'm just commoditizing it without the whole fraud aspect. So thank you kindly. I hope you enjoyed yourselves. Is there time? Yes. We have 4 minutes for questions. Come up to the microphones and be quick about it. Just start talking. Don't wait to be acknowledged. Okay. Well, have fun.